We will now look at the commands or instructions that the power computer can perform. The exact details is specific to power, but the principle is the same for other so-called RISC processors such as ARM. Okay, so again, here we have a view of the memory, and the instructions are at the lower addresses. So, and here we have lots of high numbers, and then the global variables, the heap, which grows in that direction, and the stack, which grows in that direction, and this is unused. So the PC or program counter contains an address which is an integer, which is an index into this huge array. And the int, that means the 32-bit, I mean, if it's 32 bits, the int that this PC selects in this array is the instruction to be executed next. And it is the CPU which decides that it should read the next instruction from the memory. Okay, so suppose we want to, I mean not we, but the compiler decided that it wants to add the numbers in register 12, register 29, and write the result in register 3. Then to achieve that, the compiler has produced this number somewhere here. And when the CPU reads this number, it knows what to do. We will see soon how this works. In general, the life of a CPU is to do the following. It fetches the instruction in the memory pointed out by the program counter. So it starts there, fetching what's in the current, I mean in the position that this one selects. And then it will read the contents of some registers, and then it will perform, for instance, an add operation, and then it will write back the result to, well, not write back, but write the result, but the term is write back, is, as we will come to, is to a register, and then add 1 to the program counter and repeat. We say we add 1. It depends on if we treat this as well, we add 1 word to this. So if we treat it as a byte, then we add 4, and if we treat it as an array of ints, then we add 1 to get to the next instruction. If we had a branch, then we will do something else, as we will soon see. But now we will figure out where this number comes from. When the hardware should understand what it should do with an instruction, it's essential that there is some structure to what an instruction looks like. And all the instructions in the power machine, it has 32 bits. Okay, so if we add this, it will be 32. And these bits, I mean the instruction consists of we can say sub fields or attributes and or variables. Well, we can't change them, so maybe not variables, but these attributes. And it's important that the very first attribute, if we read from left, for instance, decides what should happen next. So this, even though this instruction has the target register, the value where it should write the result. It's written in this position, and since we had R3, that position contains 3 as a binary number. Okay, and well, we can look at the operands, the other operands. 12, that's in this position, and well, this is decimal, and that is binary. Okay, and then we have 29, which is there. Okay, and some more bits, which we come to soon. So, different instructions can have different such fields. But it's important that the hardware knows where to start when it is going to interpret what to do. Otherwise it will be extremely complicated. So the first 6 bits for the power, it's called the primary opcode. The opcode is the code of the operation to perform. And for power, sometimes it's split into 2 parts. If this primary opcode contains the number 31, it tells the CPU that it should look at these bits to see exactly what it should do. So the decimal number 266 says to the processor that it should perform an add with 2 integer registers. Okay, and the other fields, when it knows that it should do this add, then it knows how to interpret these fields, and it will, then it's possible to perform this add in the hardware. These other we can ignore for the moment. And then we can ask ourselves, why is this this number in decimal? Well, it's not very strange, but we have these fields, and if we write them as ones and zeros, we get the sequence of 32 ones and zeros. And this number is simply this interpreted as decimal, this 32-bit number. Okay, sometimes we prefer to write them in base 16 instead of base 2. So and to do that we need to group them in 4 bits at a time. So each base 16 digit can have a value from 0 to 15, obviously, and then we group this in 4-bit groups, and we get this number. And if we translate this base 16 number or this and that base 2 number, we get this. So that's the explanation to where this number comes from. Okay, so there are some rules. It's the engineer or group of engineers that decide this specification. They are called processor architects. They decide which fields should be used for the different instructions and their positions and the number that tells what to do. Okay, and the primary opcode is always in the first position. IBM counts from the left, while many others count from the right, but that doesn't matter very much. Okay, so to do something else, we switch this opcode to something else. Or we can switch this opcode as well. Okay, so for this machine, all instructions have 32 bits. For x86, that's not the case. Some are, well, they have different number of bytes, these instructions. Since all instructions have the same width, it's easier to read ahead what is going to happen. Otherwise, you don't have to interpret everything in a sequence to get to the, for instance, 10th instruction that you will do next, but you can just look at that position at once. Okay, so power is an example of a RISC processor, and they are superior to CISC processors. All new computers are, new instruction, new architectures, they are designed using CISC ideas. RISC ideas. And CISC is it contains this C is for complex instruction set computer, and this is reduced instruction set computer, and it requires more hardware to make this fast. So we will next look at a very simple RISC computer, which is not the power at all, but it's just a few lines of C code, and this can be used to understand how a RISC computer works in quite detail. Okay, so let's do that next.